Hello! This is the very last video of the module and the MOOC. Today we will talk about heating and cooling grids. The learning objectives of this video are to learn the basic working principles of heating grids, which type of heating and cooling grids exist, and what their characteristics are. Furthermore, we address the main design considerations of new grids or the transformation of existing grids to be more sustainable. The main purpose of heating grids is to distribute thermal energy from a central source to distributed consumers. In such systems, water is commonly used as a transport medium, which is then transported via a network of pressurized supply and return pipes. The heating power, Q dot, in such systems is determined by three variable parameters: the mass flow rate of the medium in the pipe, the supply temperature of the medium, and the return temperature. The latter two together constitute the temperature difference at which the heat is delivered. These entities are important design parameters in heating grids. Throughout this video, I'll refer to them regularly. Heating and cooling grids have been developed since the late 19th century. Initially, these were steam grids, which supply temperatures up to 200 degrees. In second generation grids, these temperatures dropped significantly. The third generation grids usually have one or more large-scale heat sources, for example industrial waste heat, centralized biomass boilers, or combined heat and power plants. Temperatures are still typically well above 70 degrees Celsius. These conditions are typical for most of the existing large-scale heat grids. Moving to fourth generation grids, which were introduced in the early 2000s. We see the introduction of more renewable sources like solar and geothermal energy sources and other lower temperature level heat sources. As a result, the temperature further drops in fourth generation grids, but still only heating is delivered. This changes when we shift to fifth generation grids. Again, the temperature reduces further. This means that the heat supply needs to be upgraded at the individual building level. Hence, the use of heat pumps is more common in such grids, making it also feasible to combine both heating and cooling in the same grid. An important consequence of that is that the consumers also become producers of heat. Let's look at the different characteristics of the different generation grids in more detail. In the first, second and third generation heating grids, the supply temperatures are high, over 80 degrees. First and second generation heat networks are not that common anymore in the built environment, but they are in industry. Currently, in 2025, third generation grids are the most occurring types of heating grids in the built environment. They require centralized circulation pumps for heat distribution. Furthermore, since the supply temperature is high, the exact return temperature level is not important, as heat sources such as gas-fired boilers can produce any temperature that is required. When an existing district heating grid needs to decarbonize, it is foremost important to transform to lower temperature levels to accommodate the connection of renewable sources like waste heat or geothermal energy. In existing heat networks, it is costly to increase the mass flow rate capacity, as this would require replacement of pipes for bigger ones. So to keep the heating power at the required level, it requires efforts to reduce the return temperature in all connected buildings such that the supply temperature can be reduced as well. This may require increase of heat exchange capacity at the consumers and/or reduce the demand by insulation. In a fourth generation grid, lower temperature sources are utilized. As a consequence, the return temperature is lower. When the return temperature is too high, there is a low DT and with that a lower heating power, which may lead to comfort problems. Also, centralized circulation pumps are used here, so the controllability and design of fourth generation grids is similar to that of first, second and third generation grids. One of the challenges in fourth generation grids includes the integration of smart solutions. Incentives like variable tariffs can be implemented to reduce return temperature or minimize the peak demand. Since heat storage is very cheap compared to electricity storage, heat storage can be can be charged using heat pumps or electric heaters while balancing the power grid and at the same time. This is an example of power to heat integration. Lastly, in fifth generation grid, things become even more energy efficient, but also more complex. Individual buildings may use cooling from the grid, which means they automatically also provide heating to the grid. This makes the return temperature even more important to control, as other buildings may want to use that heat later for heating purposes. Another important difference is that the use of circulation pumps is at individual building level. The buildings may extract from the warm or cold pipeline following their demand, and therefore centralized circulation pumps are not required anymore. This also allows for bidirectional flow of heat between these buildings. So the fifth generation grid can supply both heating and cooling simultaneously and is characterized by a tailored and novel design concepts as compared with earlier generation grids. The novel fifth generation grids are most advanced. Therefore, more attention must be paid to the design of the control system at building level and network level. The return temperature has become a key performance indicator, and that multiple power to heat solutions can be implemented. Now, let's cover the main design considerations. 4 disciplines are required for the design of district heating and cooling grids, and they need to be considered in conjunction. The hydraulic design uses criteria for the maximum steady pressure gradient, friction losses, and results in pipe diameters, sizing of pump, valves, and surge mitigation measures. The thermal design uses criteria for the design temperature and heat loss in the network and leads to a selection of pipe material, the insulation class, and the sizing of expansion vessels. The structural design determines the thermal expansion, the soil pipe interaction, which results in a choice of pipe material, installation method, and the installation of expansion cushions if necessary. Finally, the control design aims for safe, stable, and efficient operation of the grid and results in the operational control philosophy that details how pumps and valves will be operated, such that the heating and cooling is supplied at the right temperature level at the right time. To summarize our learnings, you've learned the basic working principles of a heating grid, where flow together with supply and return temperature determine how much heat is being delivered. To ensure robust design, we have identified the 4 disciplines that are required for the design of heating grids. And lastly, we discussed the different generations of district heating, and we have listed key design considerations for making district heating grids suitable to be fed with renewable energy sources.